Hi everyone, this is the first set of solutions for practice test number 1 for your final exam, which is on Wednesday the 11th and Thursday the 12th. Remember, you are allowed to use a graphing calculator for both parts of the exam, and you will be given a blank unit circle and a trig identity sheet with all of your identities from chapter 6. Any other formulas that are covered in this video or on this practice test are ones that you need to know for the exam. All right, question number 1, we're going to convert 12.2711 to DMS, which means degree, minute, second notation. For this problem, 12 degrees is going to remain intact, but that decimal is what we're converting into minutes and seconds. To do that, we're going to start by taking our decimal, currently in degrees. If you multiply by 60, you're going to convert it to minutes. That gives us 16.266 minutes. The whole number in front of the decimal is your minutes. The remaining decimal, multiply by 60 again to turn into seconds. If you still have a decimal like this one, we're going to round to the nearest second, which would be 16 seconds. So 12 degrees, 16 minutes, 16 seconds is the final answer for number 1. Number 2, we're going to find the remaining sides of a triangle ABC that has a right angle C. Angle A is 21 degrees and side B is 1.4. So we have a right triangle in this problem. And my right angle is C. Just label my other two sides A and B. Angle A is 21 degrees. Side B, opposite angle B, is 1.4. And we need to find everything else that's remaining. To get angle B, we know that all of our angles in our triangle add up to 180. So 180, take away the 2 that I have, is going to give me 69 degrees. To get side A, I'm going to use my given angle, 21 degrees. A is opposite, 1.4 is adjacent, so I can use tangent. Tangent of 21 degrees equals opposite over adjacent. To solve for A, you're going to multiply by 1.4 on each side. Make sure your calculator is in degree mode for this. 1.4 tangent 21 gives me about 0.54 is equal to side A. Up here we had angle B, mark that. Okay, oh, I forgot to circle my answer up top too. Let's go ahead and do that real fast. There we go. All right, and then I also need side C. Again, I'm going to try to stick with my given information here. So I'm going to use 21 and 1.4 again. Side C is my hypotenuse. 1.4 is adjacent, which means I can use cosine this time. Cosine of 21 is adjacent, 1.4 over hypotenuse. To solve for C, I'm going to multiply by C on both sides first. And then I'm going to divide by cosine 21. So 1.4 divided by cosine of 21, I'm going to get about 1.50 if I round to the nearest or hundredth there. And those both would be labeled in feet if I was going to add a unit onto those. Okay. Number 3, given that secant is -7 over 6 and sine of theta is greater than 0, find the exact values of the remaining trigonometric functions. Okay, so sine of theta is positive and secant of theta is negative. If we use our all students take calculus, we can figure out what quadrant we're in. The quadrant where sine is positive is either quadrant 1 or 2. Because secant's negative, we must be in quadrant 2. So we can draw a picture in quadrant 2. My reference triangle. There's my theta. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So what I see here is hypotenuse and adjacent. One of those is negative. We know the hypotenuse is always positive, so the 6 must be negative. Pythagorean theorem will give me the missing side. So y squared plus 36 equals 49. Y squared equals 13. So y equals rad 13, and then you always want to double check if it's positive or negative. Here it would be positive again because of the quadrant that we're in. Okay, our missing trig functions. Starting with sine. Sine is opposite over hypotenuse. Its reciprocal cosecant is adjacent, or sorry, well, let's go ahead and put that there. Cosecant is my hypotenuse over my opposite, which we do need to rationalize that 7 rad 13 over 13. Okay. Cosine, this one's easy. This is one you could get without the triangle because we know it's the reciprocal of secant, just negative 6/7. I'm not going to write secant because we already had that one. Finally, tangent is opposite over adjacent. So rad 13 over negative 6. And then cotangent would be its reciprocal, negative 6 over rad 13, which again, make sure you rationalize that, negative 6 rad 13 over 13. And those are the remaining trig functions. Problem number 4, this is a unit circle question. We want to find the exact value of cosecant 15 pi over 4. Okay, 15 pi over 4, it's a little big for my unit circle. So I'm going to start by subtracting a full rotation in radians, that's 2 pi. And if you want a common denominator, we can write that as 8 pi over 4. If I do that subtraction, I get 7 pi over 4. So I want to find the cosecant of 7 pi over 4. Cosecant, we know, is the reciprocal of sine. On your unit circle, 7 pi over 4 is 315 degrees. If that's helpful, you can always convert it if you want. Sine is the y coordinate, and that would be negative rad 2 over 2. If we take the reciprocal of that, we get the negative rad 2 on the bottom and the 2 on top. We want to rationalize that, so I'm going to multiply by rad 2 over rad 2. That'll give me a 2 rad 2 on top. I'm actually going to put my negative in the numerator there. Rad 2 times rad 2 on the bottom just gives me 2. And then my 2's cancel, leaving me with negative square root 2. Number 5, we are not graphing. We're just naming the properties of this trigonometric equation. To get the properties, I would suggest first making sure that your equation's in that standard form that we practiced. And hit that standard form. We don't want anything multiplied by our x, so that 1/3 I'm going to factor out. Dividing by a third is the same as multiplying by 3. So if you imagine multiplying both numbers in this parentheses by 3, we end up with x minus 3 pi over 6, or just pi over 2. And if you want to double check that you did that right, you can just mentally distribute that 1/3 in and make sure you're back where you started. That's your A, your B, your C, and your D value for this equation. Starting with the period for sine and cosine is 2 pi over B. 2 pi divided by a third, same as multiplying by 3, gives me 6 pi. B is my amplitude, that's the absolute value of A, so positive 1/2. C is my phase shift, that's the opposite of C, so that would be a positive pi over 2. D, your domain for these functions is always the same, all real numbers. E, your range for these functions is always the same, formula, I guess I should say. So there's two things that we start with when we have a range. Whether it's sine or cosine, we always start with a -1 as my minimum and a 1 as my maximum. And then there's two things that affect the range. The first thing is a vertical stretch or shrink, which is your a value. So we're going to multiply by my a. That would give me a -1/2 and a +1/2. And then the other thing that can affect your range is a vertical shift up or down, which is your d value. So we're going to add on d. Now here d is a -3, so we're actually subtracting 3 from both of these terms. If I do -1/2 minus 3, I get -3.5. If I do 1/2 minus 3, I get -2.5. And you can always graph the whole thing if you want to. You can even play with the functions in your calculator. Remember, a good way to graph these is in radians instead of degrees. You've got radian measures anyway here. That'll give you a nice picture of it, and you can double check that range. Finally, the sinusoidal axis was y equals d. This was pretty much the horizontal line that created that vertical shift up or down. So in this problem, that would be y equals -3. That's going to go right through the center of your range. You can see there, it's going to go right through the center of your wave. Okay. Number 6, we're doing the same thing, but this will be either a tangent or a cotangent problem. So for number 5, it'll be sine or cosine. For number 6, it'll be tangent or cotangent. Again, I'm going to start by getting rid of that -2, putting this in standard form. Actually, I'll do that over here, I think. So y equals 4, cotangent, -2, factor that away from my x, dividing by -2, I'll be left with an x, and then a positive pi over 2. And again, you can kind of mentally distribute that back in and make sure it works. Okay? All right, let's start with the period. Period of these graphs is always, if it's tangent or cotangent, just pi over b. The b value here is 2. You don't need to worry about that negative. That negative does a reflection, but it doesn't change the period, so just pi over 2. Okay. B, asymptotes. We're going to come back to asymptotes in a minute, I think, actually. Let's jump to phase shift. C, that's still the opposite of C, so negative pi over 2 in this problem. D, my domain is going to be all real numbers except our asymptotes, always the same thing. And again, we'll list those asymptotes in a minute. E is our range, always the same. These are the functions that kind of look like an S shape when we graphed them. So -infinity to infinity. To get the asymptotes, actually do this in a different color, the asymptotes and the zeros, you're going to actually have to do the transformations for these. Or again, you can maybe graph it and use that as a hint to help you. So for cotangent, a place where we had an asymptote at cotangent was 0. You can find that on your unit circle at 0. Our cotangent is undefined. And then a place where we had a 0 on my cotangent function was at pi over 2. At pi over 2, the cotangent is 0. Okay, so I'm going to take those 2 points, 0 undefined, and pi over 2, 0, and do scale changes and translations on them like we did when we graphed them. And actually, you could do this and do the whole graph and find all of the properties if you want to, but we only need to do it for these 2 points to be able to figure out those asymptotes and zeros. All right, so my scale changes, the equation that we used for those was the reciprocal of b, which would be -1/2 times my x, and a times y, 4 times y. To get translations, it was x minus c, so it'd be x minus pi over 2, and then y plus d. We usually do not have a vertical shift up or down, like this one with cotangent or tangent, so it's just going to be y plus 0 or y. So transforming our points, -1/2 times each of my x's would be 0, and negative pi over 4. That's a 4. And my y's will still be undefined and 0 when I multiply them by 4. My translations, take each of my x's, subtract pi over 2. So negative pi over 2, we have an asymptote. That's what we needed to know on the transformed function. If I do negative pi over 4 minus pi over 2, think of that like negative a fourth minus a half. It's a negative 3/4. My y is still 0. So that tells me, again, on the transformed function, I have a 0 at negative 3 pi over 4. So the answers can be written now for part, I'll do this down here so we have space. There we go. For part B and part F. Part B is our asymptotes. We know we have an asymptote at negative pi over 2. And then remember the form that we did this was we wrote plus the period times k. My period here is pi over 2 times k. Don't forget that k is an integer. Okay, and to get our zeros, we're going to do the same thing. We know we have a 0 at negative 3 pi over 4, and those are going to occur every period again. So plus the period times k. And we already said that k was an integer, so we're all set on that one. All right, that was a biggie. Moving on to number 7, we want to find the exact value of this inverse function. Now, inverse functions, the answer to them is an angle. Let's call that angle theta. If this was on our unit circle, we could find theta fairly easily and then find the cotangent of that. 2/3, unfortunately, is not on our unit circle. So we're going to need to draw a picture. You need to know where each of our inverse functions are defined for. Inverse sine is defined in quadrants 1 and quadrant 4. Because the sine is positive, this angle will be in quadrant 1. If the sine was negative, it would be in quadrant 4. So I'm going to draw a picture in quadrant 1. Again, our reference triangle. When in doubt, for a lot of these problems, draw a triangle. And my sine, opposite over hypotenuse, is 2/3. Pythagorean theorem is going to give me the third side. Let's call it x. X squared equals 2 squared. Nope. Plus 2 squared equals 3 squared. There we go. X squared plus 4 equals 9. X squared equals 5. And therefore, we're going to get rad 5 for x. Once you have your triangle drawn, there's our theta. We can now say, well, this equation, we don't know what theta is, but we've got the reference triangle for it. So replace that parentheses, that innermost parentheses with theta, and now we're going to evaluate cotangent theta, which you can find any trig function now as long as you have that triangle. So cotangent is adjacent over opposite. My adjacent side is rad 5. My opposite is 2. And no need to rationalize here. Final answer. Make sure if a problem says exact value, you are giving fractions or radical answers. You should not be giving any decimal answers for those. All right, that's everything off of Chapter 5. Let's move on to Chapter 6. Chapter 6 starts with simplifying some of our trig functions. This is where that trig identity sheet is going to start to come in handy for you. All right, for this problem, we're simplifying as much as we can, hopefully getting it down to a single trig function if possible. I'm going to start, because I've got a lot of different trig functions on this one, writing it with sines and cosines. So instead of secant, I know I can write 1 over cosine. Instead of cosecant, I know I can write 1 over sine. Sine plus cosine. Denominator, 1 over cosine plus 1 over sine. Okay. The next thing I'm going to do is that term out front, you can just multiply the numerators and denominators together, so you can think of it as one big fraction if you like. We're going to distribute that in to the parentheses. So actually, let me write it out as that single fraction there. 1 over cosine sine times sine plus cosine all over 1 over cosine plus 1 over sine. All right, again, if I distribute that through, for my first term, I'm going to have sine over cosine sine. My sines will cancel, leaving me with 1 over cosine. Plus, if I distribute into the second term, I'm going to have cosine on top, cosine and sine on the bottom. The cosines cancel this time, leaving me with 1 over sine. My denominator was also 1 over cosine plus 1 over sine. So I have something over itself at this point, and I'm confident in saying that my answer is equal to 1. And as soon as you get it down to a single term, you know you've simplified completely. Number 9, given that tangent of u is 20 over 21 and u is in quadrant 1, cosine of v is negative 5/13 and v is in quadrant 3, find the cosine of u plus v. Okay, I'm going to draw my reference triangles. U is in quadrant 1, and its tangent, opposite over adjacent, is 20 over 21. V is in quadrant 3. Make sure these right angles are always on the x-axis. There's my V. And its cosine, adjacent over hypotenuse, is negative 5/13. I know the negative 5 has to be negative because that's my x value there. The triangle in quadrant 3, triangle V there, this is a Pythagorean triple, 5, 12, 13. The 12 also has to be negative, or you can do the Pythagorean theorem on that one. For U, it looks like I might need to do the whole Pythagorean theorem, 20 squared plus 21 squared equals, I'll just call it r squared, I guess. All right, let's see. We've got 20 squared plus 21 squared gives me 841 equals r squared. Let's take the square root of that. Oh, actually, that one works out nice and pretty. I get another triple. We don't use this one very much. 20, 21, and 29. Okay, so now let's go ahead and find the cosine of u plus v. You need to use your sum and difference identity for cosine u plus v. So cosine minus sine is the identity that we're looking at for this one. Cosine of u from the triangle would be adjacent over hypotenuse, 21 over 29. Cosine of v was actually given, negative 5/13. Sine of u is opposite over hypotenuse, 20 over 29. And sine of v, opposite over hypotenuse in that triangle, would be negative 12/13. Multiplying my numerators and denominators together, 21 times negative 5 gives me negative 105. 29 times 13 gives me 377. Then I'm going to have minus and negative, so I'm going to make this one a plus. 20 times 12 gives me 240. Again, my denominator is going to be 377. Add them together. Negative 105 plus 240 in that numerator is going to give me 135 over 377, which I don't think reduces, and it does not. So that is my final answer. Okay. Next, given secant of theta is negative 7/5 and sine of theta is less than 0, so negative, find the exact value of cosine 2 theta. All right, again, we're going to draw a triangle. Secant is negative and sine is negative. The only quadrant, if you look at your all students take calculus, where both of these could be negative is quadrant 3. So let's draw our theta, right angle on the x-axis, in quadrant 3. Secant is the reciprocal of cosine, so that's going to be hypotenuse and adjacent. Again, the adjacent side is what's going to be negative. Pythagorean theorem is going to give me that third side, call it y. So y squared plus negative 5 squared equals 7 squared. Y squared plus 25 equals 49. y squared equals 24, and y equals the square root of 24, which you can break that down and it will be negative. I'm going to leave it like this though, and you'll see why for the equation that we're going to use in a second here. So we're doing a double angle, cosine 2 theta. You actually have 3 different options for cosine 2 theta. You have one that just has a sine, one that just has a cosine, and one that has both a sine and a cosine. So you can use any of them. It doesn't matter. I'm going to use 2 cosine squared minus 1. But I think the ones that have just a sine or just a cosine like this one are easier because it's just less that you have to plug in. Cosine, if you look at the triangle, is adjacent over hypotenuse. So actually, I'm not even going to need, if I use this formula, that rad 24 at all. My adjacent side was -5. My hypotenuse was 7. Square it. And then you can really just type this whole thing in the calculator at this point. Just be careful with that negative. So -5/7 squared times 2 minus 1. Make sure you give a fraction answer, and you will get 1/49 is your solution. Okay. Number 11, find the exact value of the following function. So this one could come from multiple sections, as you can see here, 6.2, 6.3, 6.4. So the idea here is you want to recognize the identity that's being used. So if you replace, we've got 2 different angles here. Let's call 7 pi over 12 a u and 5 pi over 12 a v. Sine u, sine v. You can see that we get one of our trig identities. This is cosine u minus v that we see. And the u is the 7 pi over 12. And the v is the 5 pi over 12. And then you can just simplify that easier side of the equation. 5 pi over 12, or 7 pi over 12 minus 5 pi over 12 is 2 pi over 12, or pi over 6. And then this becomes a unit circle question. So cosine is my x coordinate at pi over 6. Final answer is going to be rad 3 over 2. So if you see these big complicated ones where the angle's already plugged in, take a second and try to find that on the identity sheet and use what we typically have to start, the easier side of the equation, and filling that in is going to help you evaluate this. Okay. Next, we have something from 6.3. So this was half angle and double, actually, I take that back. Yeah, half angle and double angle. We saw both of those. 6.2 was all of our sum and difference identities. So this could be either, this one's going to be a half angle. Couple things I would suggest at first here. I would use my even odd identity. I have a negative inside my cosine, which I can just drop because cosine is an even function. The other thing that we did a lot with these problems is if you had a radian, you converted it to degrees just to make it easier to see the angle that you had half of for the half angle. So if you multiply by 180 over pi is how we converted. The pi's are going to cancel. 7 times 180 divided by 8 gives me 157.5 degrees. There we go. At this point, the 0.5 should be a dead giveaway that you're doing that half angle identity. So the next thing we're going to figure out is what angle divided by 2 is the same as 157.5. So you can just work backwards and double it. 315. That's going to be the theta that we use in our half angle identity. So here's the half angle identity for cosine. You don't have a choice on this one. It's 1 plus cosine theta over 2. And then we just have some simplifying. So in this problem, plus or minus square root, it's going to be 1 plus cosine 315 over 2. From your unit circle, you should know that the cosine of 315, the x coordinate at 315, is a positive rad 2 over 2. To simplify this, we multiply inside, underneath the radical, by 2 over 2. So that's going to give me plus or minus. If I distribute the 2 on top, I'm going to have 2 plus 2 times rad 2 over 2 just gives me rad 2. In the denominator, 2 times 2 gives me 4. Then we can take the square root of the numerator, which doesn't simplify any more than what you see there, and the square root of the denominator. Square root of 4 just gives me 2, so that gets rid of the radical. And then the last thing we have to think about is it going to be a plus or minus? And to figure that out, you can just look at this original angle that you had after we got rid of the negative. You could even look at the original problem if you want. Cosine of 157.5. So 157.5 is an angle in quadrant 2. If you have a cosine in quadrant 2, you know that your answer is negative. So you could do that at the very beginning if you want to determine if your answer is going to be positive or negative instead of bringing that plus or minus all the way through. Okay, I think we're going to stop there with a dozen problems for the first video. Check out video 2 to see more.